It's the year 2000. You are part of a mining crew pumping water out of a cave in Chihuahua, Mexico. Suddenly, you notice a shard of crystal. You enter the cave and suddenly you're surrounded by gigantic crystals called selenite. Welcome to the Sierra de Nika Cave.
The type of crystals found in the Nika mines is selenite. Selenite is a form of gypsum. Its proper name is calcium sulfate dihydrate. When people see these giant crystals, their first thought is usually, how did they get so big? To understand this, you first have to look at the cave as a whole to understand the conditions under which the selenite was formed. The type of crystals found in the Nika mines is selenite. Selenite is a form of gypsum. Its proper name is calcium sulfate dihydrate. When people see these giant crystals, their first thought is usually, how did they get so big? To understand this, you first have to look at the cave as a whole to understand the conditions under which the selenite was formed. Then you must look at the chemical makeup of the selenite crystals. So what were the conditions? Well, due to this cave's location on a fault, magma was able to flow up high enough to heat the cavity, which is full of groundwater. This groundwater contains calcium sulfate dihydrate. As temperatures rose, the molecules broke apart. This is because there is water bonded to the gypsum, which is what makes it a hydrate. Water has hydrogen bonding, which is strongest at cooler temperatures. So when the heat rose, it weakened and the molecules began to break down. Once the temperature of the water dropped to around 58 degrees Celsius, or 331 Kelvin, they began recombining into selenite. The gypsum crystals remained underwater, so they were able to keep growing until they reached the size they are today. This diagram demonstrates the structure of gypsum crystals. Blue represents calcium, yellow represents sulfur, red represents oxygen, and pink represents hydrogen. Within the calcium sulfate, there are two types of bonds, ionic and covalent. Calcium and oxygen are bonded ionically due to their 2.4 difference in electronegativity. Calcium is quite willing to transfer its valence electrons to oxygen. The sulfur and oxygen are bonded covalently. They have a 0.8 difference in electronegativity and share the valence electrons. Believe it or not, these gypsum crystals are relatively soft. This is because there's water incorporated into the structure. The water creates distance between the calcium ions and the sulfate ions, which weaken the strength of its ionic bonding.
Crystals are unique in that they have a very special arrangement of atoms. They're uniformly spaced throughout, and this gives them their geometric construction. Because of this, the structures are able to deflect powerful rays like X-rays through them in a way that amplifies them and allows them to be recorded. In the early 1900s, scientists discovered that crystals diffract light predictably and developed the equation wavelength equals 2d sine theta that relates the wavelength of the radiation, the diffraction angle, and the lattice spacing, or the spacing between the building blocks of a crystal. This equation and method was used to identify crystalline structures and help discover and investigate many new types of crystals and crystalline structures. Scientists then discovered that this method of diffraction could be used for discovering things other than crystals, such as the structures of proteins and DNA. This is the method Watson and Crick used to create their famous model of DNA, and has led to many other important discoveries in pharmaceuticals, energy storage, or batteries, and even about the atom itself. I can't conduct an experiment in X-ray diffraction because it would require me to get my hands on a diffractometer, but I can show you how it works on the whiteboard.
Here's the structure of the crystal. This allows the diffraction to occur, and the uniform spacing is really important to the equation later used. First, the X-rays come into the structure and hit the atoms. Some of the light hits and diffracts, while the rest keeps traveling and will later hit and diffract in the same manner again. This diffraction will cause an angle to occur with the horizontal of the structure. This is referred to as theta. This angle of diffraction made with the horizontal will have a special relationship to the distance between the atoms, d, and will form d sine theta. It'll also have a relationship with the wavelength of the radiation used, or lambda. This creates the equation n lambda is equal to 2 times the d of sine theta, which allows you to discover things about the structure of the crystal.
These selenite caves hold wonders the scientific world has yet to encounter, and using crystal diffraction may just help scientists find out amazing things about the abilities and structures of these giant crystals.
In the giant crystal caves, scientists have run several different tests to look deeply into microorganisms living in the crystals. These organisms are unofficially called bubble bugs because they don't have a scientific name yet. Floating in pockets of fluid, the microbes are likely new to science and maybe up to 50,000 years old, according to a NASA researcher. Contamination during drilling with microorganisms attached to the surface of these crystals or living in tiny fractures constitutes a very serious risk. In order to ensure that there is no contamination of the crystals when drilling into them, we took many cautious procedures, including wearing protective suits, sterilizing the drills, and in some cases, even using fire. The results were outstanding. Due to poking into the fluid samples, we were able to wake up the dormant organisms which were said to be sleeping for a very long time, which is extremely impressive since humans can only stay for about 45 minutes inside the caves. These creatures thrive on iron, sulfur, and other chemicals that have been found trapped inside the very toxic environment of the giant crystals. The results of this research have led scientists in other departments of research to change the way they think about finding life on Mars. They are now trying to develop new strategies that involve digging deep, not into the surface of Mars, but into the subsurface, where the microorganisms can be found.
Due to the extreme conditions inside of the caves, it is very difficult to explore them or learn about them. When explorers entered the caves in the early 1900s, because of the conditions inside, one of the men died and the other one barely made it out alive. This can be attributed to the hot magma that rests underneath the caves, causing them to heat to intense temperatures, around 120 degrees Fahrenheit, and humidity around 80% or higher. So, experiencing a heat stroke while inside the caves is almost inevitable. Once the body reaches 98.6 degrees Fahrenheit, it begins to sweat. But because of the high humidity, the body can't regulate its temperature by perspiring. When you sweat, water is excreted out of the pores in your skin, evaporating once it's on the skin's surface. However, with high humidity, there are too many water molecules already in the air, which prevents the sweat from evaporating and in turn, failing to regulate your body's temperature. Recent scientific studies also show that high heat temperatures can cause slower cognitive functions and reaction speeds, as much as 13% slower, which could be dangerous in a situation like this, where being able to think clearly is essential, especially when figuring out how to leave the cave. When your core temperature reaches 99.5 degrees Fahrenheit, the hypothalamus, which is sensitive to temperature changes, signals the rest of your body to release heat, which happens to be done by sweating, but as we know, sweating isn't effective in the cave's environment, and this leads to your brain straining to try and make your body sweat. But because sweating isn't resulting to a decrease in body temperature, mental fatigue can occur and makes it more difficult for an explorer to escape the cave.
Humans play a big part in why giant crystals of the Nika cave can no longer grow. One of the reasons this cave no longer supports the growth of giant crystals is due to our changing climate. Humans have greatly contributed to the progression of our Earth's climate change. In order for crystals to grow, the cave must be at a specific temperature. Changes in our Earth's climate causes temperature fluctuations underground. Scientists believe the Nika cave to be 500,000 years old, so it has undergone quite a few changes in its time. For hundreds of thousands of years, this cave was filled with water, which allowed these giant crystals to form. However, it is now dried out due to miners at the Nika cave accidentally draining the cave. Due to this, the giant crystals can no longer be formed and crystals will start to break. The crystals have nothing to support them now that they have been devoid of water, which will cause breakage and destruction. The discovery of the Nika cave is surely one to go down in history. Like many occurrences in the history of our planet, the environment of this cave is constantly changing, so we must enjoy its beauty while we can.